point is vector b, which was transferred before, as I above mentioned. And this is a law for vector addition. And scalar multiplication is defined as the following way. If we have some vector a and some real number lambda, the scalar product lambda and vector a is the such vector which denoted by lambda a is defined in following way. If its length is equal product of module lambda and length of vector a, this vector is parallel to the vector a, and its orientation is coincide with orientation of vector a if lambda greater or greater 0, and this vector has the opposite orientation if lambda is negative number. Lambda a is the same, lambda a has the same orientation if lambda is positive number and lambda a has opposite orientation if lambda is negative number. This is a definition of this operation, and we are going to solve some problem which help us to study this operation maybe less better. Let's start this exercise 1. Let's given an equilateral triangle ABC with AB is equal 6. Find find the length of these vectors. So we have some equilateral triangle, and in the equilateral triangle we have the length of each sides are equal 6, and we also know the measure of the angles in these equilateral triangles. Each angle is equal 60 degrees, and the vector EAC and ratio 1:3 of AC, this vector, let's denote the endpoints of this vector by maybe C1, and let's AC1 is equal ratio 1:3 multiply on the vector C. By definition, this vector is parallel to vector C, and this vector has the length exactly just 2, and this vector has the same orientation as the vector AC by this definition point, maybe A, 2, 3, by item 3. Okay, and vector AB, this vector, and difference between these vectors, these vectors BC1, and we are going to calculate the length of these vectors. How we can to calculate this length of this vector? We can use cosine theorem, which gives to us the way to calculate the length of side in triangle if we know two other sides and angle between these sides. The cosine theorem asserts that square of length of third side is equal sum of squares of length of first two sides A and B minus is twice product of length of the sides on cosine of angle between the sides, and we can use this theorem and calculate the length of the vector BC1, and we obtain the answer in the form I'm sorry, the length vector BC1 is equal the length of this vector is equal sum of squares plus AB minus multiply on cosine the vector cosine of angle phi, which is equal 60 degrees. And substitute the length of this vector, the length of the vector a c1 is equal to the length of vector ab 6 and twice product of length of this vector 6 2, and as well known, cosine of 60 degrees is equal half 1 ratio 1 2, and after the simple calculations, we have the square. We obtain we obtain 28. 28. Okay, and after simple simplification, we obtain that the length of vector bc1 is equal root square and is equal twice root square for 7. And bc1 is equal the difference of vector ac, which multiply 1 ratio 1 3, and vector ab, and the answer and this problem is solved. Okay, this simple application of elementary geometry formulas and theorem for calculation for vectors. But later we will use only some native formulas of vector algebra, and we need to develop some technical matter that use some problem of elementary geometry without theorem of elementary geometry. We reproves some basic assertion of elementary geometry using only technique of vector algebra, and will be later. And now let's try to solve one more same problem and calculate also some length of some vector. Maybe maybe this following exercise. Let's solve. We have some arbitrary triangle ABC. ABC, and let M ABC is a triangle. M be a midpoint of the side of the side BC. Of the side BC, and let's given AM is some vector x, AM x is given vector, and AC is given vector y. And express AB in terms of x and y. Express AB in terms of x and y. More precisely, we would like present this vector as a linear combination of the vector x and y. Why we can do it? The answer is following. This vector AC and AM is not collinear vector, and then these two vectors form the basis in the plane, and this fact guarantees for us that we can express any vectors in a plane as a linear combination of these two vectors. And in this case, we must to find some exact linear combination which gives this expression, is presentation of the vector, the arbitrary vector, in our case the presentation of vector AB as a linear combination of these two vectors. How to find this linear combination? Let's look for some relation between these vectors, and after them we try to find some exact expression for vector AC. We can see that the vector, for example, vector BC is equal differences of vector AB and AC is equal AB minus AC. In this expression, AC is given vector y. Is given vector y, but AB is unknown vector, and we will continue to look for some relation between this vector and other. We can see that vector BC is equal twice C. Oh, I'm sorry. BC. BC. Oh, I'm sorry. CB. CB is equal difference AB and AC. CB. CB is equal twice vector CM, and vector CM can be expressed in terms of vector AC and AM. CM is equal AM minus AC. It's okay. AM is X and AC is Y, and we obtain the exact expression of vector Cm in terms on given vectors. And if we substitute this expression in previous expression, we obtain that CB is equal twice difference x and y to x minus to y. Okay, and vector the question is AB. Using this expression, we can express AB as the sum CB plus AC. CB. Yes, CB. AC, yes, and we can substitute the expressions for CB and AC and obtain CB is equal to multiply x minus twice y and plus y and the answer is twice x minus y. And in this for solve this problem, we need only some transformation of vector, which we did using only properties of vector operation, vector addition and scalar multiplication. But we know that such expression exists, and we use some general theorem which assert that this expression exists for every plane vectors, because every two non-collinear vector are form the basis in the plane, and this basic theorem. Let's try to solve some problem which use coordinate presentation of the vector. I recall that if we have two vectors E1 and E2 in a plane, or three vector E1, E2, E3 in the space, and in this case we have two non-collinear vectors, and in the second case we have three non-coplanar vectors, and in this case these two vectors are form bases in the plane, and in this case such three vectors form bases in the space. What means that vectors are form bases? This means exactly that if we have arbitrary vector x, exists unique linear combination of this vector which is equal this vector x. In other words, we can decompose the vector x by vectors e1 and v2, and coefficients of this decomposition is called coordinates of vector x in the basis e1, e2, and in the plane. For the case of plane, in the case of our three-dimensional space, we also the same decomposition for every vector x, and arbitrary vector x can be represented as a linear combination of the vectors e1, e2, and e3, and coefficients of this decomposition, which we denote by x1, x2, and x3, is called coordinates of vector x in the base e1, e2, and e3. In both cases, such decomposition exists and unique. And coordinates also uniquely defined by bases. If we fixed some bases, we can uniquely define coordinates of arbitrary vectors in the space or in the plane, and we obtain some correspondence between vectors of vector space. If x arbitrary vector of maybe v2, let's denote it by geometrically the set of geometrical vectors which parallel some plane. For us is a geometrical plane, and for if x is an arbitrary vector, we can assign to these vectors the pair of real numbers which these real numbers are the coordinates of this vector in the base E1, E2. And let's denote that this correspondence by letter phi is below index E, where E denotes these bases in the plane. And this pair is the element of arithmetical vector space R2. And the same picture in the case of the space. We also have the same correspondence between geometrical vectors of space and triples of real numbers, such that the vector x is a linear combination of basis vector with coordinates x1, x2, and x3, and we correspond to this vector the coefficients of this combination, and this triple is the element of arithmetical vector space R3. In the Boy's case, we can also correspondence between vector operation in the vector space in the left side and the operation between 2 or 3 tuples of real number in the right side of our correspondence. I recall, if we have 2 vectors x and y, and if we decompose each of this vector on vector of basis, and in the first case we have the decomposition xy, x1 e1, x2 e2, so vector x and y is equal y1 e1, y2 e2, and after them we can, using the properties of the vector operation, namely commutativity property and associativity property, we can permutate the summands and obtain this expression. After them we can use distributivity property and we obtain the following expression. Thus we can see that to sum of the vector in the vector space correspond the coordinate sum of its coordinates. namely we obtain that our mapping corresponds to the sum of vector xy, the vector which coordinate is equal x1, y1, x2, y2. So we obtain Да-да, извините, у меня сейчас лекция. Да, добрый день. We have the following equalities. So we obtain the following equality. The mapping phi transform the sum of vectors x and y into the sum of its images. And this main conclusion from the properties of the basis, and we will use the coordinates of the vector to calculate some characteristics of the vector in the terms of coordinates of the vector. So if we choose basis in the space, we reduce the problem on vectors, geometrical vectors, to the problem for calculation of some expression using the coordinates of the vectors, and reduce the geometrical problem to the arithmetical or algebraical problem. And let's try to solve the following problem using the coordinates. Sorry. Let's choose the basis in the geometrical space with orthogonal or perpendicular vector, and let the length of this vector is equal unit. Namely, let E1, E2, and E3 bases such that the length of this vector is equal unit, and this vector perpendicular one another. in the case of the space. In the case of the plane, we have only two such vectors, E1 and E2. And I recall that the length of this of arbitrary vector x can be computed using the following formula. And we also define, have defined on the previous lecture the so-called scalar dot of two vectors by formula. And using formulas for dot of scalar product and formula for dot length of the vector, we can calculate the angle between two vectors, namely cosine of such angle is equal ratio of scalar product the product of the length of these vectors, and in the coordinate form we obtain these expressions. We will use these formulas for some calculations, and let's formulate some problems. The first. Let's U, the vector is coordinate 2, minus 2, 3, and V has coordinates 1, minus 3, 4, and W has coordinates 3, 6, minus 4. Let's calculate the length of vector 3u minus 5v plus w. And item B, let's calculate 3 length of u minus 5 length v plus length of vector w. Compare these two expressions. First of all, let's find the coordinates of these vectors. We use the notation 2, minus 2, 3, and denoted these numbers of coordinates or coefficients of linear combination. We use transformation of geometrical vector v in the vector of arithmetical vector space. In the left side, the geometrical vector and sign of equality identify this geometrical object with arithmetical object, the element of arithmetical vector space. And we use this correspondence which was defined before. And in the right side, we can calculate the coordinates of this vector. How to calculate? We multiply the coordinates of vector u by 3, coordinates of vector v by 5, and after them we subtract from first one, second one, and to adding the coordinates of vector w. And operation we are doing on using every coordinates. 3 easy to see. We 3 multiplying 2 minus 3, 5, 1. 3 multiply by 2 minus 5 by 1 plus 3. And this first coordinate. The second, minus 6 plus 15 is equal 9, and plus 6, and obtain 3 minus 2 minus 5 minus 3 plus 6. And for last coordinates, 3 multiply 3 minus 5, 2, and plus minus 4. And we obtain 6 minus 5, 1 plus 3, 4, minus 6 plus 15 is 9, 15. And minus 4, minus 20, minus 24, plus 9, 15. And we obtain that the coordinates of this vector is equal 4, 15, 15. And after I am finished, and after them easy to check the sum of squares of this vector and obtain the answer. In this case, we can also calculate each length of these vectors and fulfill the algebraic operation and obtain the answer in this case. Oh, excuse me, my time is over. My fault. Thank you for attention. Goodbye. It's second my fault. Oh, let's continue. Let's continue. Okay. Thank you. Minus 15. And let's continue and calculate this sum. And after the simple calculation, we obtain the root square for 466. This is the length of this vector. And let's calculate the length of each of vector. The length of vector u is equal to 449. Is equal root square from 17 from V. And from W root square from 61. And we obtain that the sum is equal you can roughly estimate this sum and roughly estimate this. And we can compare these two sums. This sum is greater than 20, and this sum is smaller than 0. Roughly speaking, the sum is more than 25. This sum is less 4. This sum approximately, and this rough estimate -5. rough estimate. And we can see that this essentially different expression, essentially different. And we'll use some more complex properties, more complex definition, and let's to solve some theoretical problems. Let's express some vectors as a linear combination of some other vectors. Vectors are given in coordinate forms. Let B, vector B has the following coordinates: 24, -5. Vector A1 has coordinates 2, -1, and A2 has the coordinate 5, 1. The problem is to find coordinates of vector B in basis of A1, A2. This vector non-parallel because if this vector will parallel, each vector have the proportional coordinates, but we can see that ratio of 5 to 2 is not equal the ratio 1 to -1. So these vectors are non-parallel, and they form the basis in the two-dimensional arithmetical vector space. And we can express the vector B as a linear combination of this vector. More precisely, exist unique defined two numbers, lambda 1 and lambda 2, such that we have the equality B is equal linear combination of vector A1 and A2 with coefficients lambda 1 and lambda 2. We can rewrite this equality in coordinate form, and we obtain the following equality. Using the property of operation vector addition and scalar multiplication, we obtain that the vector B is equal to the vector with coordinates to lambda 1 plus 5 lambda 2, the first coordinates, and the second minus lambda 1 plus lambda 2. These vectors are equal if and only if its corresponding coordinates are equal. in our case we have the following equality. The equality of the first coordinates we can rewrite in the form of some linear equation, 2 lambda 1 plus 5 lambda 2 is equal 24, and equality of second coordinates we can rewrite in the form of the same linear equality, namely minus 5 is equal minus lambda 1 plus lambda 2. And we can solve this equality and obtain the exact value for coordinates lambda 1 and lambda 2. And so we can obtain the linear combination, the composition of vector v in linear combination of vectors a and 2. Easy to see that using the second equation we can express lambda 2 as lambda 1 minus 5 and substitute this expression in the first equation, and after then we obtain 2 lambda 1 plus 5 multiply lambda 1 minus 5, and we obtain 7 lambda 1 minus 25, and lambda 1, 7 lambda 1 is equal 49, and lambda 1 is equal 7, and lambda 2 is equal 7 minus 5 is equal 2, and we obtain the answer lambda 1 is equal 7, lambda 2 is equal 2. Substitute. We can check our calculation. 7 onto 14 plus 10 is equal 24. It's right. Minus 7 plus 2 is equal minus 5. Right, also. And I have 10 minutes. 10? Без 5. 15. Okay, we can try one more exercise. Let's try to solve some let's consider the following theoretical exercise. This following exercise is part of theory of vector space. Proof. that if vectors v1 and v2, the set of this vector v1 and v2 is linearly independent, and v3 does not lie in span v1, v2, I denote by this bracket the set of all linear combination of the vector v1, v2. Then v1, v2 and v3 is linearly independent. We will say the set of vectors is linearly independent. In the same sense, the vectors v1, v2, v3 are linear independent. Is the same meaning. Let's prove this assertion. What means the linear independence of the vectors? It means that linear combination of this vector is equal to 0 only if all coefficients of this linear combination are 0. Let's consider the sum linear combination of the vector v1, v2 and v3. And let this linear combination is equal 0. We want to prove that the all coefficients of this combination are equal 0. Suppose that coefficients lambda 3 is not 0. In this case, we obtain that lambda v1 plus lambda 2 v2 is equal. I'm sorry. Suppose that lambda 3 is not 0. Then I can express v3 as a linear combination of other vector. I can transfer this summons into right sides, and I can to divide with coefficients on lambda 3, and I obtain, after this simple transformation, the equality, the ratio lambda 1, lambda 3 v1 minus lambda ratio lambda to lambda 3 v2, and I express vector v3 as a linear combination of vector v1 and v2, and this means that vector v3 lies in the linear in the span of vector v1 and v2. The span is a set of all linear combination of these vectors, and we get contradiction. The vector v3 does not lie in the span of this vector. We obtain that coefficient lambda 3 must be equal 0. Must be equal 0. Lambda 3 is equal 0. And so we obtain the combination of vector lambda 1 and linear combination of vector v1 and v2 with coefficients lambda 1, lambda 2 is equal 0 vector. But the vectors v1 and v2 are linear independent. And by definition of linear independence, we obtain that these coefficients are equal 0. And if we join both this assertion, we obtain that from equality of this linear combination 0, it follows that all these coefficients are equal 0. This means that these vectors are linear independent, and we solve this problem. And maybe one more exercise. One more exercise. For example, let's solve the following enough simple exercise. We have two vectors, v1 with coordinates 1, 2, and v2 with coordinates 3, 4. First of all, show that the set v1, v2 is a basis. For R2. To find the coordinates vector vector v 5, 6 relative to the basis. let's try to solve the item 1 of this exercise and show that the vector v1, v2 is a basis for R2. We can to prove this fact using the various way. First, maybe simplest way to prove this fact to use that the fact which is the following fact: every two non-collinear vectors are form the basis in the plane, and we can easy to check that two vectors are non-collinear because the ratio of these corresponding coordinates are not equal. And from this we can deduce the linear independence of this vector, and every two linear independent vectors are form bases in the plane. The second way to prove this fact, we can prove that these two vectors are linear independent, and we can prove that every vector can be expressed as a linear combination of these two vectors. For this, we can first of all let's consider some linear combination of this vector, and let this linear combination is equal 0. We can show that the coefficient of this linear combination are equal 0. Easy to see that linear combination in coordinate form has the following form. And this expression we can rewrite in the form of equality of two vectors. One of them has the coordinates lambda 1 plus 3 lambda 2, and second coordinate 3 lambda 1 plus 4 lambda 2, and this vector is equal 0, and we obtain the system of linear equation in the following form. We can to solve this equation and obtain that all unknown lambda 1 and lambda 2 are equal 0. And so we have proved that these vectors are linear independent. And the second fact why this vector are form a basis in the vector space. Let's consider arbitrary vector with coordinates x1 and x2, and we can solve this system from such right side, and we can explicitly express the coordinates lambda 1, lambda 2 in terms of x1 and x2, and we can obtain exactly exact expression for this coordinate, and this reasoning to prove that this vector are from the basis. My time now is up. Thank you for your attention.